Hello, this is Panagiotis Bouros from Johannes Gutenberg University Mainz, and I'm presenting our joint work with the University of Constance titled Most Diverse Near Shortest Paths. This is the outline of my talk. First, I will discuss the motivation behind our work and previous works in the context of alternative routing. Then I will formally define the problem of finding the most diverse near shortest paths and briefly describe our proposed evaluation methods. Finally, I will discuss the findings of our experimental analysis and conclude my talk with ideas and directions for future work. Alternative routing has been already proposed as a way to recommend to the users a set of diverse paths instead of a single path. Most of the existing works operate under the assumption that path length is an optimization criterion and path dissimilarity is the constraint. However, this way we may end up recommending to the users paths that are too long. Take, for example, the picture to the right. The user requests two paths from Zurich to St. Gallen. One option will be to recommend the black and the red paths, which are very dissimilar to each other. However, the red path is also very long. A different option will be to recommend the black and the blue paths, which are more similar to each other compared to the black and the red paths. However, they are both shorter than the red path. Another problem is how to set the dissimilarity constraint, usually using some kind of threshold. And this is actually counterintuitive for the users. It is hard for the users to understand the semantics of a 50%, for example, threshold, or the difference to a 40% one, even if they are aware of the similarity measure that is used. Our proposal is to consider path length as the constraint, which guarantees the quality of the recommended paths in terms of their length, and path dissimilarity as the optimization criterion. Regarding previous works in alternative routing, one direction is, as already discussed, to consider length as the optimization criterion and similarity as the constraint. And this includes the k-shortest paths with limited overlap and the k-dissimilar paths with minimum collective length. Another direction is to consider both these aspects of the paths as optimization criteria. To the best of our knowledge, there is only one work that does this, and this is called the k-diversified shortest paths. However, similar to other works in multi-criteria pathfinding problems, there is a high computational cost, and also we might end up recommending paths that are too long or too similar. A different direction will be to first compute a large set of candidate paths, and then on a post-processing step, apply the constraints and the optimization criteria to come up with a final set of recommended paths. And this direction includes the plateau method, the alternative graph, the concept of single via paths, and the concept of Pareto optimal paths, also known as route skyline. A final direction would be to use iterative approaches, such as the penalty-based method or the direct method. In this work, we propose a range of solutions, and for some of them, we build upon some of these ideas. For example, we discuss how we can use the concept of single via paths to recommend k most diverse near shortest paths, how we can apply the direct method, and how we can build upon the penalty-based method. But before we go into details about the evaluation methods, let's first discuss the problem definition, formally define the problem. The input to the problem is the graph of a road network, a source and a target node, the number of requested paths k, and the positive number epsilon to define the length constraint. The result of a KMDNSP query is a set of exactly k near shortest paths, meaning that every recommended path has a length of 1 plus epsilon times larger than the length of the shortest path. And among all sets of paths that satisfy the first condition, the result set has the highest diversity, which is defined equal to the lowest pairwise dissimilarity among the paths that are in the set. We can use any similarity or dissimilarity definition for this problem without a loss of generality. In our work, we use the Jaccard coefficient. We also proved that this problem is NP-hard, and we came up with a range of solutions, including an exact solution and 3 heuristic-based solutions. And let's start with the exact solution, or the exact approach. Essentially, it consists of 2 phases. During the first phase, we need to compute all near shortest paths. And during the second phase, we need to examine these paths and generate candidate k subsets to identify the one with the highest diversity. For the first phase, we rely upon the path enumeration process described by Carlisle and Wood. We traverse the network in a depth-first fashion, and we filter out subpaths that violate the nearest shortest path constraint with respect to epsilon. We can actually enhance this pruning by estimating lower bounds for the path extensions, which can be done by pre-computing the shortest path from every node of the graph to the target. For the second phase, we rely on the filling-Rasak dynamic programming algorithm described by Knuth in his textbook. Essentially, we incrementally build a binomial tree, and this tree represents all subsets with up to k near shortest paths. We can actually further enhance this process by defining a pruning criterion to prune unpromising subsets. And the idea is that every time we add a new path to an existing subset, its diversity can only drop. So if we already have a candidate solution, we can actually filter out all subsets that have a diversity already lower than the diversity of the candidate solution. So this is a simple and straightforward approach, but has a very important shortcoming. It has to compute a large number of near shortest paths, and this affects the cost, not only of the first phase, but also the cost of the second phase. We will need to examine all these paths and generate the k subsets. And we expect the cost of this method to be exponential, and the method to be also impractical for real-world networks. The solution is to come up with a number of heuristics that will trade the quality of the result, meaning the diversity of the result set, for performance. And the key is to reduce the number of computed paths. So let's discuss the first idea towards this direction, which builds upon the concept of the single via paths. So a single via path of a node n essentially is a concatenation of the shortest path from S to N and from N to T. And we extend this concept in case the single via path contains cycles, and we introduce the concept of simple single via paths, or SSVPs. So now let's see how we can use SSVPs to enhance the computation of the query at hand. So we can actually modify the first phase of the exact approach, and instead of computing all near shortest paths, we can compute all near shortest SSVPs. And this is what we call the SSVP-based approach. We can compute all these SSVPs by pre-computing the shortest path tree from S to every node in the graph, and the reverse shortest path tree from every node in the graph to the target, or from target to every node in the graph. The second phase of the algorithm remains unchanged. And since the set of all near shortest paths is much larger than the set of all near shortest SSVPs, we have actually reduced the search space and accelerate the query evaluation. We can further accelerate the evaluation by considering a sufficient number of near shortest paths and build upon the penalty-based method. Essentially, we apply this iterative approach, and on each round, we compute one near shortest path P, and we penalize the edges that are contained in P, and then repeat the same process. Every time we penalize the edges of a path, we force the search to follow a different way. And we can further optimize or enhance this process by using dynamically adjusted penalties. The second phase again remains unchanged, and this is what we call the penalty-based method. So it is obvious that SSVP and penalty-based approaches build upon the same principle as the exact method. They both operate in two phases. However, they reduce the search space because they have to compute a much smaller set of near shortest paths. However, they still need to generate candidate K subsets, which is also an expensive step. That's why we propose a third solution inspired by the direct method proposed by Cheng and al. In 2009. The idea is to incrementally build the result set in k-1 rounds. Initially, the result set contains the shortest path, and then on each round, we consider the last recommended path P, and then we modified it to construct a new near shortest path P prime, which has the highest dissimilarity to all already recommended paths. And then we recommend this path and continue. Essentially, we only need to construct k near shortest paths to construct the final results. Now, we implemented all these methods in C++ and experiment with 5 real-world road networks with different sizes and topologies. And our experimental analysis essentially answers 3 questions. Is exact practical? The answer is no. It can only be used with tow networks that contain up to some hundreds of nodes. It's already orders of magnitude slower than the heuristics. How good those heuristics are and how good they scale. SSVP can handle networks up to only 100,000 nodes, whereas penalty and direct can handle even statewide networks. And finally, how good the results are of the heuristics. Of course, the exact approach produces the best result. So the best heuristic is SSVP, followed by the penalty method. To sum up, we introduced a novel instance of the alternative routing problem, recommending k near shortest path with high diversity. We propose an exact solution and 3 heuristic-based solutions with different properties. For the future, we plan to further investigate the evaluation using other types of algorithms, for example, flow algorithms, and consider alternative paths, alternative definitions of path diversity, or even visualize the results. Thank you.